I've given you. 17C. All you need to know is that in 17C you can use, so sampling, you can use normal distribution, so normal approximation, to binomial again. That is very similar to exercise 16E. So for those who aren't even up to that yet, 16E essentially is similar to 17C. Okay, 16E, 17C. Now, there was a rule that I mentioned in 16E and I did it wrong in the notes and I told you to fix it. This is the correct one. I think in 17B there was also a miss part of the question that was also wrong there too. So just make sure that in my notes when I put an extra P there, cross it off. It should be N times P and N times not P. That's pretty much the condition. So when can you use normal approximation for a binomial, so meaning continuous random variable to predict for a discrete random variable? It's when N times P and N times not P is greater than 5. Okay, that's according to your textbook, and that's what VCAL will be looking for. So they ask you to show that it's a normal approximation, prove that you can do this, that this is what you'll be proving that it'll work. Okay? So normal approximation to binomial distribution, then that condition must be met. Now a bit of language, just so that you understand the rules here. This is your table of guidance for chapter 17. Chapter 17, we had a look at 17B yesterday where I went through quite a bit of theory there. Talk about small sample, small population. It's hypergeometric. What is that again? That is to do with the combinations rule. Okay? Versus large population, but small sample. And how do we know? The condition is that it needs to be less than 10% of the population. So if the sample is smaller than 10% of the population, we can then assume it's large enough. And if it's large enough, we're going to assume the probability is consistent. So it's constant. If it's constant, you can then use binomial distribution. Okay, so if it's binomial, then this is your new rule. That's your expected value. So the expected value of sample proportion becomes the actual population proportion. Okay, so if I said 80% of year 12s like gaming, then that now becomes each sample that I grab, that's 80%. I expect 80% of it. Okay? Whereas normally, if it's a small sample, I won't use that because each group will have a different proportion. Okay, so this is when samples vary. This is when samples stay consistent. Then you have your standard deviation, same thing. This one is following your discrete understanding. Okay, so that's what we did yesterday. Today, we're now in this column. Okay, so now what happens when you have a large population, so same thing, but what if your sample size is not small now? What if it's big? So how do you know if it's big enough? Ryan, thank you. How do you know if it's big enough? This condition up here. Okay, large sample, large population. Make sense? So we had small population, small sample, large population, small sample, and now we have large population, large sample. How do you know if it's big enough? That's a condition. Yeah? So if it's big enough, if it's greater than 5, it is big enough. And if it's big enough, you can then make that approximation. So this is the condition. You can then make that approximation that you can use normal distribution. If you can use normal distribution, then essentially you do the whole mean, standard deviation and all that. So how do you find mean? Same thing. Mean is the same thing as before. It's still equal to P. Okay, and that's what my notes are saying here. So this is 17C, just to help you understand. 17C, so when it's large enough, so remember large population, you can then make that assumption. All right, and what's the next one? This one. So standard deviation, that's 17C. Now, why am I calling these 17C? Just to help you differentiate. Notice the language I'm saying here. One says mean of sample proportion. One says mean of sample successes. A way to sort of understand the notation here, think of successes when you were doing chapter 14. You count the number of successes, so it's discrete. So it's like your X random variable. So it's mean of X. That's chapter 14. Yeah, NP. Whereas sample proportion, that's the one that Albert was asking before. That's P hat. Okay, so P with a hat, that's talking about a proportion. So by definition, if you didn't pick up yesterday's lesson, P hat, by definition, is your sample success, number of sample success, over your sample size. So if I'm picking 3 students, how many people have an iPhone? So last time I picked 3 students, we had 2 out of 3. That was one particular proportion for one group. Does that make sense? That's one group of 3. So this is one definition that you probably want to keep in mind when you start doing conversions. But with that property, that's how they got these extra 2 formulas. Okay, notice that the n disappeared in this one, and that disappears as you divide it by n. It cancels out. Same thing with this one. Notice the difference between these 2. That's where it comes from too. Okay, but in a nutshell, what do you need to know? Simply, this is chapter 14, binomial, and this is chapter 14. Cool, so that's binomial, binomial, sample proportion. Sample proportion is what I'm trying to highlight. Nutshell good? Okay, good. Flip over, because now we're going to do an example. So this was just a summary, just to see that you can see the difference between them all. All right, flip over. Here we go. 17C, this is question 9. We did modify it just slightly, but same idea. Here says the proportion of voters in the population who favor candidate A is 52%. Okay, and then of a random sample of 400 voters, 230 indicated that they would vote for candidate A at the next election. So let's break it apart. As you're reading this question, when they say the proportion of voters in this population favor candidate A is 52%, what are they saying here? What's 52%? Rango. 0.52 is? Good. Now, in terms of the chapter 17, which we only learned so far 2 key terms, population, sample. You learned population parameter, which is the letter P. You learned sample proportion, statistic, or sample statistic is called P hat. Which one is this one? What's 0.52 equal to? Which one is this one? Is this the population proportion, or is this? It is population proportion, because if you read even in the sentence itself, it tells you the population who favor candidate A. They're telling you the target audience overall is 52%. But what's this? 400 voters and 230. See, I selected a sample. I chose an X amount of people. I took out a random sample of 400 voters. This here is n equals 400. And out of those 400 people, so my sample proportion, P hat, this is P. Okay, this is P. P is 0.52, that's 52% population proportion. My sample proportion is out of 400, 230 favor candidate A. So here, 230. Do you see the difference between the two? It's the language. So 17A was getting you to know the difference between population and sample. Population is target audience. Sample is me grabbing something out of that target audience. So here, how many people did I grab out? 400. Out of those 400 people, 230 favored candidate A. Whereas the first statement, that was not my sample proportion. That was my population proportion. Cool? All right. Now, usually they don't sort of guide you with part A, and you're meant to figure this out. But part A tells you already. Show that the normal approximation is appropriate in this case. How do you know that this is appropriate? What do you have to check? How do you check? What do you check? In order for you to use normal approximation, how do you know when it's appropriate? What do you check? Pat. Beautiful. When you multiply these two, it should be greater than 5. That's what we're looking for. If it's greater than 5, then we can actually use it. So let's calculate. NP. What is this? What's our case in this case here? Let's go calculator. Sample size is 400. N is 400. And P, what's P? Very good. So 400 times P. Remember, P is up here, 0.52. That gives us 208. That's bigger than 5. That's good. Next one, 400 times not P, which is essentially what? 400 times 1 minus 0.52. 192. Oh, sorry. Let me do that again. 400 times 1 minus 0.52. Both greater than 5. Therefore, normal approximation for this scenario is appropriate. Okay. Larger than 10%. So we know it's a large population, large sample. It's not a sample of 3, it's not a sample of 2. Large population, large sample. Test if you can use normal approximation, and yes, you can. Answer the first question. B, what is the value of the sample proportion p hat? What's the answer for this one? What's my sample proportion, Pat?
Is it 230 over 400?
Yeah, that's my sample proportion. So in this case here, p hat, which we answered as we were reading just now, p hat is equal to 230 over 400. Let me just, still, no, that's as small as possible. 23 over 40. Yep. All right, let's write that. 0.575. Sweet. So we've got our value of the sample proportion. Now today's lesson, what's 17C about? Just to type it in and practice. We're trying to show that we can use normal approximation to solve. But let's go. What is the standard deviation of the sample proportion? Look at your notes on the front page. How do you find the standard deviation? If you know now that P, it's a large population, what's the standard deviation formula again? Square root of?
E times 1 minus P all over E.
Beautiful. You already got P. You already got N. So here we go. Square root 0.52 times 1 minus 0.52, which is really 0.48, divided by 400.
And it's 400, not 230, because it's the entire population, not the sample size.
Well, this is the sample size.
Yeah, but you use the entire population, not the sample. Because the samples, I don't know, yeah.
Yeah. Sample size is 400.
Yeah.
And then that's the chances, because remember, when it's large enough, then the population proportion is then assumed for the sample proportion. Yeah. So we're using it as to find a standard deviation of the population proportion. All right, let's go. What's the answer? What do you guys get? Square root 0.52 times 0.48 over 400. You get 0.02497. So now you know how to find standard deviation using the formula. You've already got sample proportion. Let's answer this question here. Find. Notice the key word. Approximate. When you see the word approximate, you should then be thinking about 16C or 16E, or in this case here, 17C. So approximate probability that in a random sample of 400, so I still got N equals 400, the proportion who favor candidate A is greater than or equal to the value of P hat observed in this particular sample. Now that language was very difficult, so I already typed what the language is trying to say. But if you don't look at my typing, could you have figured that out? See, I typed in what the actual thing was trying to ask you to do. Okay, so had I not typed this for you, could you have read that line and understood what it was saying? So breaking apart, sample of 400, so you know N equals 400. The proportion, so when you think of proportion, you got to think it's got to be a fraction. Who favor candidate A, okay, so proportion of candidate A is greater than or equal to. So how do you start that? So I started off by saying, what's the proportion? So chances of P hat favoring candidate A. Well, I had 230 people that favor candidate A, but they wanted equal to or greater than the value of the current sample proportion. This is what I'm currently observing. Okay, so 230 over 400 is what my current P hat is. That's what this is. So far, so good, boys? Settle down. Let's focus. Yeah? Especially when I get to 17D, I don't want you to be mucking around. So here we've got P hat. I want to know what's the proportion when it is greater than the current P hat observed. So I'm essentially saying I want the chances of my proportion to be greater than or equal to 230 over 400. Now, ideas. How do we solve this? Someone else besides you. You've been answering all the questions. Say that again. Inverse norm PDF. There's a lot of words that you're saying there. Almost. Let's just think. We're doing approximate. We know we can use normal approximation to do this. Dante? Is it the mean? Yes. Somewhere there. It is meant to be greater. Boys. Thanks. Don't speak while I'm speaking. Thank you. Let's draw the picture just so you can picture what's going on. Remember, in this scenario, you know it's a normal approximation. You can approximate because it's large enough. So let's draw a picture, right? Here's our population proportion, p hat. What does it mean again? Not 6.5? 5.2. 5.2 is our mean. This is what we expect of the population. Yeah? So remember that property E of p hat equals p. In our case was 0.52. I expect this is where the mean is. So this is what Dante was saying. So that's where the mean is. So it has to be greater than, right? Where's the proportion that I'm looking for? I'm asking for the p hat to be greater than or equal to the current p hat. The current p hat of proportion is 230 out of 400. Now, Pat told us before that's 0.575. This is 0.52, so 0.575 is somewhere over here. So let's draw it. So if I draw it in, I say, all right, 0.575, that is my current proportion. But what do they want? They said from this point or greater. So they're asking for this. They're asking, find the probability. When I ask you to find the probability of the proportion greater than or equal to 230 over 400. That's what it's asking. Now that I've drawn a picture, what do you do now? So let's go back to Joe again. I've got a picture. How do you find this area? Norm CDF. See, that's the correct wording now. Not inverse norm and not PDF, whatever you said before. In this case here, we now know what to do. See what I mean? So draw the picture, think about the problem. So here, this is just norm CDF. Norm CDF working from a boundary of 0.575 all the way to positive infinity. What's our mean? 0.52. What's our standard deviation? You got it over here. 0.02497. Type that on the CAS. Let's do an approximate. Here we go. So you already got standard deviation. I'm just typing out the CAS, working out for it. So norm CDF, you got the boundary. You know the mean, you know the standard deviation. So type it in your CAS. Here we go. Type it into my CAS. Menu 5 distributions. Norm CDF this time. Lower boundary 0.575 or 230 over 400, up to you. All the way to infinity. Mean was 0.52 and standard deviation was 0.02497. Do you guys get roughly this answer? 0.0138. So roughly about 1.3% or 1.4%. Okay, so the answer there, what's the approximate probability? The approximate probability is around 0.0138. Yeah.
If you're doing it with proportions, are you able to go up to infinity, or do you have to stop at 1?
Oh, because this, I usually go to infinity just because it's a continuous. Yeah. Yeah, so it will still be pretty close, but I usually just go to infinity. Yeah. So far, so good? Yeah, because I'm trying to do a quick express so that I can get onto 17D. That's 17C. So 17C is finding mean, knowing when to use it, standard deviation, knowing how to use it, and then just reading that. That's the hardest part. Being able to interpret what the question's asking. Drawing it helps. Drawing the scenario and then reading into it, that helps you to understand what the question's asking. Cool? All right, if you're not, this is all on OneNote at the moment. You can copy that down later. We're going to move our news into 17D, and I'm just going to show you how. The how, and then I'll make a video on the why. Okay, I'll make a video on the why, and then you guys can watch that on Tuesday. Okay? All right, can you please now grab out the new notes for today, 17D. Let's grab that one out. I'm going to stop the video